Okay, the recording started, so please, Victoria, go ahead. So the floor is yours.
All right, thanks. Yeah, so I'm Victoria Goliber from D-Wave. As I mentioned, I'm based in Germany, so quite close to some of you, I suspect. So I'm going to be here with you all morning, and so we're going to go through quite a few different things. Hopefully you can follow along. If you don't already have a free Leap account to access D-Wave solvers, I would suggest that you go ahead and sign up for one right now. I'll drop the link in the chat. So if you go to that site, there should be a sign up and you can, get a free account, get access right away. And so you'll be able to follow along with like the demos and the exercises that we'll do this morning. And then there's some more hands-on exercises in the afternoon as well. If you already have a Leap account, great. If you already have a Leap account and used all of that free time, there is a way to renew that each month so that you can get a little bit extra. And I'll show you where to do that once we get started. So let me go ahead and share my screen. It looks like I need to give some permissions because I have a new laptop. And I have not used Teams in a while. I'm going to have to drop the meeting really quick and join back in. Is that okay, Ricardo?
Okay, no problem, no problem.
Okay, I'll be right back.
Yeah, we're going to wait for you. Let's just wait for Victoria because she's having some issues with her laptop.
All right, I'm back. Sorry.
Okay.
I got a new computer a couple of weeks ago, and this is the first time I've had to share a screen in Teams, and so you have to give permissions for that. So hopefully this should work now.
Yeah.
All right, we will share that. And can everyone see my screen?
Okay. Right now, I don't.
You don't see the screen.
And also, you look like freeze. I mean, your webcam looks freeze.
Let's see. Let's try it again. Any luck this time?
I know. But
it says presenting.
Okay. I can try to change your status from participant for just a second, and then back to speaker, just to see if this goes away.
Okay.
Hi, Victoria. You should be now allowed to speak and share. I don't see your webcam. And I also cannot hear you. You look things muted. Victoria, we see. Okay. Let's try.
So, good morning, everyone. Can you hear me?
Yes, Daniele, but we don't see you.
Today.
Also, Victoria has some problems.
Can you hear me now?
Yes,
Yeah,
we
we
can
can
hear
hear.
you, but we cannot see you. So I have a problem also that says that to unconnect the video camera. Oh my God, but what is this morning? Let me see if... You're right, Riccardo.
So you can hear me, but you can't see me.
Exactly. I think that I have the same problem. I'm trying to leave the meeting and enter again, maybe.
Let me try sharing my screen, because if you can see my screen,
yes, exactly.
It says I'm sharing now. Can you see?
No.
No.
Not at the moment. So. This is a really strange behavior.
Okay,
oh,
now
we can see you.
You can see me?
Yeah.
Exactly. Hi, Victoria.
Hi.
But you
We
cannot
still can't see you. No, and we still can't get my screen.
One pizza star. Oh, fantastic.
Okay, now we see
You
you
see
and
it?
the screen.
Okay.
Exactly.
Okay.
Perfect.
You cannot see me, but it's not important. Okay, we can start. Thank you, Victoria.
Okay.
Thank you.
I don't know what is
Fantastic.
going on. I did nothing different, but if it works, great.
Very good. These are quantistic effects.
All right. Everything good?
Yeah.
Seems to be good. Yes.
Okay. So I am, once again, I'm Victoria Goliber. I'm here from D-Wave to lead this morning's session. So a little bit about me. I'm a senior technical analyst. I'm part of the European team. So as I mentioned, I'm based in Germany. I've been with D-Wave for almost 5 years now and spent most of that time working with customers, teaching classes, presenting at conferences, doing workshops and seminars. So lots of time spent with people learning how to use the tools, learning what you can do with them, and really seeing how they can bring value to their business with quantum. So today, hopefully, I'll give you a bit of an idea of what that's like and how to run some programs and get your hands dirty with everything that we have available. We have a schedule here. I think maybe you all had this information shared. We should have a couple 15-minute breaks scattered throughout. I'll do my best to stick to this schedule. This morning, we're going to start with the constrained quadratic models and D-Wave's hybrid solvers. The constrained quadratic models are very easy to get started with. They allow you to feed in your problem as math equations that you're used to. You don't need to do as much manipulation of the model that you're building. So it's a nice, easier way to get started. Our hybrid solvers, these are using both quantum and classical resources. And these, again, are a nice, easy way to get started because there's not very many parameters that you need to worry about tuning to get good results. Then we'll take a break, and then we'll move into the binary quadratic models and running problems directly on the quantum computer and the quantum hardware. So you can get a feel for what some of these parameters are like and how you can model a problem to submit it directly to the quantum computer. Then we'll take another break, and I'll go over just a couple customer use cases, what some people are doing with these solvers and the tools available. And we'll wrap up with any questions. We should have plenty of time for questions at the end. Please also feel free to ask questions throughout. I will do my best to keep an eye on the chat when I can, and we'll hopefully get any questions answered.
Don't worry, we will tell you the questions if
Perfect. Thank you. All right, so let's just dive right in with the constrained quadratic models. As I mentioned, this is a really nice, easy way to get started in using our hybrid solvers. So I'm going to really dive in with these hybrid solvers. So I believe you all had some background on like the quantum hardware and the annealers and everything. So I'm not really going to dig too much into that. Instead, we're going to really focus on how you use it. What do the models look like? How do we build the models? And how do we write Ocean programs, Python programs to send them to the solvers? So the first class of solvers that we'll look at, this is the hybrid solvers. As I mentioned, these run both quantum and classical resources. So you can kind of think about it in your mind as you have this really, really big real world problem, and it's much bigger than a quantum computer. And you want to figure out which parts of this problem are best suited to the quantum hardware and which parts can be run pretty efficiently classically. And so this is going to basically take sub-problems and run them on the quantum computer, while classical optimization is taking place in the background. So it's going to use both resources to solve your problem. And so this enables you to run problems that are much larger than the size of the hardware, that use different like variable types and problem formulations than you would need to use if you were running directly on the quantum hardware. So we have 3 different hybrid solvers available in our portfolio: the constrained quadratic model, the binary quadratic model, and the discrete quadratic model solver. Now, they all sound really similar except for that first word, constrained, binary, or discrete. And this really has to do with like how you're formulating your problem. So starting with the one in the middle, the binary quadratic model solver, to use this one, you're going to formulate your problem as a binary quadratic model. What does that mean? That means binary, all of your variables are binary, 0, 1 variables, and it's going to be quadratic. So you can have linear terms and quadratic terms made up of those binary variables. And in this model, basically, you need to come up with one mathematical equation to represent your entire problem. So when we talk about a problem, generally we're talking about optimization problems. These generally consist of an objective or a couple objectives, something that you're trying to maximize or minimize, and a set of constraints. These are like the rules that need to be satisfied for a solution to be feasible. And so for this binary quadratic model, you're going to wrap this all into one equation with up to 1 million binary variables, and you'll send that over to the hybrid solver. That's the binary one right in the middle. The discrete quadratic model solver is similar, except you have a different type of variable that you can use. So instead of just binary variables where you can only take 2 values, 0 and 1, a discrete variable can take any number from a set of values. So you could think about this as like the integers 0 through 10. You could think about this as colors from the set red, green, blue. Basically anything where like your variables are choosing their value from a fixed finite set of choices. And those are discrete variables. And again, this is going to be a quadratic model. So, linear and quadratic terms using those variables. You're going to wrap everything up into one equation, like I mentioned. And this is going to handle smaller problem sizes up to 5,000 discrete variables. You can do quite a lot with that because you can have, I think it's up to like 10,000 values for those discrete variables. So you get quite a large problem even with only 5,000 discrete variables. And then last but definitely not least, this is probably our latest and greatest hybrid solver, the constrained quadratic model solver. Now this one, your variables can be binary, they can be discrete, and they can also be integer or even continuous. So this allows you a huge amount of flexibility in how you're defining these variables and how you're looking at your problem. With those variables, it's still a quadratic model, so you still have linear and quadratic terms using those variables that you've designed. However, in this case, you don't need to wrap everything up into one equation, which makes it really easy to use. So you can individually define your objective, what you're trying to minimize or maximize, and you can individually define constraints like, the sum of the variables has to be equal to 12, or the cost is less than or equal to some budget that I have. So you can have this whole list of inequality constraints that you don't need to wrap up into one equation. So we've made it quite a bit easier, which we'll see as we dig into some of the exercises. And this model, you can run problems with up to 500,000 variables and 100,000 constraints. So this is really quite large, complex problems that you can now feed in and run on this hybrid solver. So as I mentioned, this continuous variables is an option with this CQM solver. And this is one of our more recent updates to this hybrid solver. So previously, when we first released it, it was just, binary and integer variables. And now we've added in continuous variables because that was something that people were asking for quite a bit. It really makes it a lot easier to more natively represent your problem when you don't have to take something that should be a continuous variable and, discretize it and do binning and things like that to make it kind of fit into binary or integer variables. Now you can simply define it as a continuous or real variable. So still allowing you to do the same number of variables up to 500,000 and up to 100,000 constraints, but now adding in those real or continuous variables. So there's a lot going on here. So I thought we could start with an example of how we can put this hybrid solver, this CQM solver, to good use in the real world. So a really hard problem that comes up a lot is 3D bin packing. So this is related to, if you have big trucks that you need to ship goods from a warehouse to retail stores, or you have, an Amazon delivery truck, you need to figure out how to efficiently pack boxes into these shipping containers to fit as much as possible. So, if you have to use an extra truck, that's going to cost you more money. So you want to fit as many boxes as you can to use as few shipping containers as possible. So this is a problem that comes up a lot in many, many different applications. And the goal is essentially you have this whole list of boxes that you need to fit into a set of containers. You need to figure out which container should each box go into. You need to figure out where within that shipping container you should place the box. And then you need to figure out which orientation. So, you can turn a box and sit it many different ways. And so you need to figure out all of those things to figure out how you're going to pack these shipping containers. And so this is really going to use both binary and continuous variables. So if you think about the question, which container am I going to put each box in? If I have a box that I need to choose which container to put it in, and I have 3 containers to choose from, that's a nice discrete choice, right? I can put it into 1, 2, or 3, and those are my only options. Once I've chosen the shipping container, where to place it in 3D space inside of that now is a continuous decision, right? So I can put it anywhere in 3D space that's available inside of the shipping container. And so this is where my continuous variables are going to come into play. So this is going to use a mixture of the different variable types that we have available in our CQM portfolio. So this is a pretty complicated problem for those of you that have some background in, computational complexity. This is an NP-hard problem. I think just packing one shipping container, I believe, is NP-hard. And so when you add in multiple containers, it just becomes a lot more difficult. So it's a very challenging problem that people have to face pretty much every day in business. So how would we solve this using our hybrid solvers? We have like a vague problem description here, but we need to come up with a more specific technical description so that we can mathematically model this. So what does that look like? The way that our team chose to implement this, there are a few different ways that you could probably describe the problem. We chose to describe it in this way. So our objective is made up of 2 parts. This is, the minimize, maximize component. And so the 2 parts of the objective, the first one is that we want to stack the boxes so that they're packed down towards the floor as much as possible. Okay, so we don't want like boxes floating in space or kind of balancing on an edge where they might fall. So the way that our team worked on that was to minimize the average height of the boxes, so kind of push everything down towards the floor to pack it more densely, and then also minimize the total height of everything. So again, packing it down towards the floor more so that things aren't really floating in space. We also wanted to minimize the number of those shipping containers or bins that are used. So as few of those as possible. So those are the objectives, what we're trying to minimize or maximize in our problem. Now, what are the constraints? So this problem has a number of different constraints. So first I mentioned you need to choose an orientation for each box. You know, each box has 6 sides that it could sit on. So that's a discrete choice of how am I going to rotate the box to place it in a shipping container. Then I need to assign each box to a container. So each box needs to go in exactly one shipping container. So that's a constraint there. We need to ensure that wherever we place the box inside the shipping container, that the entire box dimensions are within the boundaries of that shipping container, right? So we can't place it in a corner where, you know, half the box is hanging out the door. It needs to be totally inside the shipping container. Then we need another constraint that says, you know, each box gets assigned its own space. I can't have any point in space where 2 boxes are assigned because, you know, they're 3D objects, they can't overlap. So that's a really important constraint as well. And then last but not least, our team looked at this from the perspective of placing boxes into containers in an order that they're given. So for example, you know, boxes are coming off of an assembly line or coming out of a warehouse. They come in a certain order, and that's when we need to figure out where to place it. And so they do come in a specific order. So this is the technical description that we focused on for this problem. I think there's a lot of different ways that you could model this problem depending on the real world scenario, right? So for example, this place boxes into containers in order. That might not be the case in some real world warehouses. You may be able to, you know, pick and choose which boxes you want to pack when from a shelf. You might have a different objective, you know, instead of stacking boxes from the floor upwards, maybe you want to do something like minimize the amount of empty space in a shipping container. You know, there are lots and lots of different ways that you could mathematically model this problem. And some are going to be better than others. And so this problem formulation and how you choose to model the problem is a really, really important part of figuring out how to get the best results possible with these solvers. All right, so let's go ahead and run this problem. And for those of you that did sign up for a Leap account and everything, you should be able to run this with me. So I'm here on my Leap account. And so for anyone that wants to follow along, go ahead and sign in on your account. As I mentioned, if you've used up your like 1 month of free time and you want to refresh this, you can click on your name at the top and settings. And in there should be a place to put in a GitHub URL for your GitHub page. If you input that there, it should, in like a couple minutes, it should refresh that usage so that you'll be able to participate later. So go ahead and sign into Leap if you haven't already. And here I am on my dashboard, which shows me, you know, how much time I have available, how much time I've used. So this is starting with the hybrid solvers. So you can see I haven't used any hybrid solver time in this account yet. And if I go and select direct QPU total, this is where I can see how much time I have available left. So if you signed up for a free account, you get 1 minute of QPU time or 20 minutes of hybrid solver time. So you should see like 1 minute here. You can see things like problem status, so past problems that I've run. You can see your usage statistics. So if I look over like the last 90 days, you can see, you know, I did a bunch on the 18th, and this account has been pretty quiet. Then there's a bunch of different solvers that are available for you to use. So I mentioned, you know, we have these hybrid solvers, and then we also have the quantum computers themselves. So in Europe, we have one quantum computer. In Germany, one of our Advantage systems, and everything else is in North America. So here are these 3 hybrid solvers that I mentioned. We've got binary, constrained, and discrete. We're going to use this constrained quadratic model. And then you can see for the QPU, we've got a bunch of different Advantage systems online. We have a prototype of our Advantage 2 system, so a small chip. And then the 2000Q system, this is a lower noise technology with a smaller chip size. All right, shall we choose online resources and application development resources? I'm not sure where that is, but I will show you where we can go to get the demo. So up at the top, we're going to click on resources. And here's your application development resources. And I'm going to scroll down and go to code examples and notebooks for this demo. So in here, this is where we have tons of different code examples for you to take a look at. This is running on both the hybrid solvers and the quantum computer. Lots of different applications, everything from puzzles like Sudoku up to, real world problems like reservoir management and things like that. So right here, I have at the top of my list 3D bin packing, or you can search for bin packing if it's not right there for you. So if I click on here, I can see a little bit about the problem. So this is some of, how the problem was formulated and everything that we just went over, and then what to expect from the demo, how to run it, and all of that sort of information. I'm just going to go ahead and click Launch an IDE, and this is going to open this demo in my web browser. So basically, this is allowing me to do all of my programming and everything right in my web browser without having to install any Python packages or anything on my computer. So for getting started and everything, the IDE is really, really useful and easy to get started. For this demo, you can see it set up to spin everything up and get the demo running so that we can see that nice picture like we saw on the landing page. So this is installing some additional packages that this demo uses, and then it should open up a new tab or a new page that shows the interface for running the demo. So we'll just give it a second to finish installing these packages. This is installing in this specific workspace. So there was a question that says, is this installing in our cloud user? And yes, basically, each one of these instances, when you open up a workspace, so I just opened up a brand new workspace. It's pretty much standalone, this is kind of an isolated virtual environment where everything is just kind of tied to this repository. So if I open up another workspace, it's very isolated, and that's its own with its own set of packages and that kind of stuff. Does that make sense? All right. So it's not launching for Claudio. Sometimes just try closing the workspace and making a new one, or there should be a URL here if it's just not opening up a new web page. Just try copying and pasting that URL in a new web page. Sometimes there's a pop-up blocker or different error messages pop up. All right, so here is the demo page. This is the interface to build up the scenario that we want to look at. So we're going to run a few different scenarios to get started. Here you can see I'm going to run a random problem, and then we've got two solvers available for you to run. We have our CQM hybrid solver that we were talking about. And then CBC is a classical open source mixed integer programming package that's used fairly commonly. I'm going to set a random seed so that it's running the same instance when I try to compare between the solvers so that they're given the same problem. Now let's go into, this is the actual situation. So we've got a time limit, the number of bins or those shipping containers, cases, these are the boxes that I'm packing in the container, how big they are, and then what are the dimensions of my shipping container. So to make things interesting, I'm going to change a bunch of these settings. So feel free to go along with me and do this. So I'm going to change this to 6 seconds for the solver time limit. This is the minimum time limit allowed for our CQM hybrid solver. So we're just going to have it run just a really short, quick run and see what the solutions look like. I'm going to run it first with just one shipping container so that we can look at that and see how it looks. And then these dimensions are really, really big. So I'm rather than give it like a huge container with just a small number of boxes, I'm going to shrink it down so it's more interesting. So I'm going to do 20 by 8 by 8. So it's more representative of like a standard shipping container like you would see on the back of a truck. And then this is going to be too many cases to fit in there. So we will just go down to like 14 cases and make them a bit smaller. All right. So I've got 6 for the time limit, 1 shipping container, 14 boxes with dimensions ranging from 1 to 6. And then my shipping container dimensions are 20 by 8 by 8. And then I'm just going to click run. And so this is going to run on our hybrid solver so we can take a look at the solution that we get. Claudio, I would try closing and deleting the workspace and opening a brand new one. So if you just close that tab and then go to Claudio, if you go to your thing and go to IDE workspaces, you can delete the old workspace and you can just start over again. Sometimes it just does that weird error message. All right, so this ran really quickly because we just gave it a time limit of 6 seconds. So here you can see this is what my packed shipping container would look like. All right, so there's still a fair amount of space, but you can really see how things are packed down towards the floor rather than like floating in space. There are a couple here where like I probably wouldn't like this gap under here for that under the purple box. That doesn't look very stable, but overall it looks like a pretty good packing. You can see for this instance where we just had 1 shipping container and 14 boxes, it required 630 binary variables and 43 continuous variables. So you can see that this was really like, it sounds pretty small, like 1 shipping container and 14 boxes, but when you actually go to model it, there's a lot more that goes into it that we need to take into account. All right, so let's keep everything here the same and just run it on the classical solver and see what happens. So if we run this, keeping everything the same, giving it the same problem, we can take a look and see how this one does. All right, so you can see the variable counts and everything are exactly the same. It was given exactly the same model, the same formulation and everything. But what we see is that there's a lot more like floating up towards the top, right? So that objective of minimizing to push everything down towards the ground wasn't we didn't get as good of a solution as we did with the CQM solver. So the classical solver, it got a solution, it fit within the shipping container. However, it's not satisfying what we wanted to minimize, that overall height. It wasn't as good as what we saw on this CQM solver. So we can definitely do better using the CQM solver in this case. Now, what happens if we increase this number of bins to 2? So this is where things start to really get interesting. On the hybrid solver, were we supposed to get the same result with the same parameters in seed? No, so our solvers are all probabilistic and the classical solvers are like this CBC is probably a heuristic. So this is an NP hard problem. So you're probably going to get different answers every time. And so you really want to look at that objective to kind of gauge the solution quality. So like how much are things packed down was our objective. So you probably did see a slightly different answer on yours running with the same solver in the same setup. All right, so the number of bins, if we change this to 2, so now we've got 2 shipping containers. So we can fit more boxes. So let's change this and bring this up to 20 and make them a bit bigger. So now allow the dimensions to go between 1 and 8. And then we'll keep everything else the same and we'll run it with our CQM solver. Let's go ahead and run that. And so now we'll have 2 containers that we need to pack, which really makes this a more complicated problem. So we're still just giving it the 6 seconds and letting this run. All right, so what we see in this case is these containers, it's hard to see. So they're side by side. So this red line is indicating, you know, the divider between the two shipping containers. Those red lines are kind of the boundaries. And you can see we packed it pretty full. The boxes are a bit bigger because we allowed larger dimensions. But once again, you can see for the most part, things are like packed towards the ground. There's a few like here where things are floating a little bit, but there's not very much like empty space towards the bottom, which is what we like to see. So I don't know if you all noticed, but down at the bottom on this constraints section, this is telling us, you know, how many linear and quadratic terms we have in these constraints. In the single container, the single bin case, this quad was 0. And so these quadratic terms, these are really the interplay between multiple shipping containers. Those decisions where like, if I put it in one shipping container, then it can't go in the other. So there are these relationships that are between the shipping containers, and that's really what these quadratic constraints are considering. So now if we switch this over, keeping everything the same, switch it over to the classical solver, and we run that, let's see. So now we actually get an error because most of these mixed integer programming, these solvers, these open source solvers like CBC, actually can't handle those quadratic interactions. So once we start adding multiple shipping containers, it's beyond the scope of what these classical solvers can handle because of those quadratic terms. Now, there are like closed source software packages that you can purchase and everything that could look at these. We were really just looking at open source ones that you could easily compare. And so we did not find one that we could use these quadratic interactions. So just a little bit of interesting things there of what you can and can't do with the, you know, the open source classical solvers. All right, so I have a question that says, can the model include some internal physics, center of mass of the bins, fragility, etc.? Your model can include anything that you can formulate in that quadratic model framework. So if you wanted to include things like the center of mass of the bins, what's fragile, those sorts of things, you could absolutely, like you could have an indicator variable that says whether a box is fragile or not. And if it is, then it has to go on the top. Yeah, there's all sorts of things that you could add in there. This is just kind of like a pretty basic intro working of what it would look like. All right. So hopefully that gave you a feel for, you know, what we can do with these solvers. So let's dive in and look at how can we write a really simple program? How can we solve some of these optimization problems using these solvers? So I think you covered a lot on quantum annealing and what it is and what the hardware does and how it works. So just a really quick reminder, we're really looking at optimization problems. And you can think about that as like a landscape of peaks and valleys where you're trying to find the lowest valley. So when you're standing in a valley, it's really hard to see and tell if there's a lower valley on the other side of the next hill. And so we think about classical solutions as kind of walking over the tops of those hills to see if there's a better solution on the other side. Now, walking up those hills is very energy and time intensive. And so this is really where we see a lot of struggle and pain points on these classical algorithms. Quantum annealing, on the other hand, can use quantum effects like tunneling to kind of see through the hills and see if there's a lower valley on the other side. It can kind of hand waving, but you can kind of search the whole space at once and really look through everything to see if there's some really good low points. So really what we're focusing on is optimization. How do we find those minimum points? And so to do that, we're using these quadratic models like I mentioned earlier. So for all of those models that I talked about, they all contained the words quadratic models. And so what that means is that we have, you know, some function that we're trying to find the minimum value of, and that function includes linear terms, these q's, and quadratic terms, which are, you know, products of variables. And you can think about this in your head as, you know, you have individual qubits on the chip, and then you have pairs of qubits that are coupled together. And so that's really where this requirement for the quadratic models comes from, is this structure of the chip. So this is why this is kind of the baseline for all of our problem formulations that we're going to look at. So when we formulate a problem, we choose what our variables are, and we can control these A's and these B's. These are just, constant numbers, they're coefficients. That's what we choose to model our landscape. And then the solver is going to return the values of these variables at, the low points, at these low points that we're looking for. Now, as I mentioned, these solvers are probabilistic. So for most of these solvers, you're going to get back a sample set, a whole set of solutions of, Q0 equals 0, Q1 equals 1, Q2 equals 1, that kind of thing. And then you're going to want to go through those. You're going to run the problem a number of times to have the probability of getting a really good result. So keep in mind, it is probabilistic, so we will run it numerous times. So for these quadratic models, this looks really, really simple. It's a pretty basic math equation where we just have linear and quadratic terms, but you can do a lot with that. So I just showed you how you can do that complex 3D bin packing problem, and there's a lot more. There's a whole bunch of NP complete problems that you can formulate in this way, and there's a great paper by Andrew Lucas if you're interested in NP hard, NP complete problems that goes through how you can formulate all of those using a binary quadratic model. So let's go through and see how we can actually formulate problems, these optimization problems, into this math form. So I have a nice development process that allows us to go through a few key steps to run our problem on these hybrid solvers. So the first step is writing out your objective and constraints just in words in your problem domain. So that's like that technical specification slide I showed you where we said, okay, our objective, we're trying to minimize the average height. We want to minimize the total height. We want to minimize the number of shipping containers. We need to just write out clearly in words what are our objectives and what are our constraints. Going from, the general description of the 3D bin packing to that technical specification slide, we had to make a number of decisions. So for example, like the question that came up, could we take into account what's fragile and things like that? Those are all decisions that we have to make. And so we need to make sure that we write out clearly the objective and constraints so that all of those are taken into account. And we've kind of formulated the problem as it makes sense for our problem domain. So once we've done that, we can define whatever variables we want. So we've got binary, integer, and now also continuous for our problem. So the way I like to do this is I think about, okay, what information do I need to make my decision, right? So for bin packing, I need to know which shipping container should each box go into and where in the shipping container. So I'm going to define variables that give me that information. So I'm going to have a set of variables that say which shipping container it goes into. And then I'm going to have a set of variables that say these are the 3D coordinates in real space of where I'm going to place the box. So keep in mind, what are you trying to get? What information do you need to get out of this problem to make your decisions afterwards? And that should help guide how you choose your variables. Once I've chosen my variables, then I can kind of combine steps 1 and 2. I'm going to take those written words, objective and constraints, and define them as math statements using those variables that I defined. And once I've done that, once I have, a list of math equations, what is my objective in math? What's the math equation that I want to minimize? What are my constraints as either equality or inequality statements, those sorts of things. Once I have those written out, I can build my model in Ocean very, very easily using the tools that are available, which I'll show you. So let's go through these steps and see what this looks like going through in order. So we'll go through the knapsack problem. This is one that some of you may have heard of before. So basically this is, again, a packing problem. However, this time I don't really care where things are packed. What I care about is I'm choosing the best things to pack. So I have a backpack that I can throw things into, and it has a weight capacity. So I need to make sure that I don't exceed the weight capacity, but each item also has a value. So I want to fill it so that my backpack has the most value, but I'm not overweight. And so basically we can split this up into an objective and a constraint. My objective is I want to maximize the value. So maximize that sum of the values that I'm putting into my backpack. And then my constraint is that the total weight has to be less than or equal to the weight limit, right? I don't want my backpack to tear and everything to fall out. So we must make sure that that constraint is satisfied. So this is what I mean, formulate your objective and constraints in words in your problem domain. Here I just have clear statements in words that say exactly what I need to do, what do I need to maximize or minimize, and what rules need to be followed. So based off of that, I'm going to define my binary variables. And in this problem, I'm going to use binary variables because what I need to know is I need to know which items to pack in my backpack. So basically, for each item that I have, I need to know, should I pack it or not, which is a binary decision. Do I take it? Yes. Do I not take it? No. So I'm going to define binary variables, one for each item, and it's just going to say whether I pack it or not. And so doing that, I can then work through and formulate my objective and constraints into math equations. So here you can see the variables. I define a binary variable for each item. This is saying, do I pack it? Yes or no. My objective, maximize the value of the items I'm packing. So here you can see I have my binary variable times the value of that variable. So if I'm packing it, this is 1, and I'm going to count the value. If I'm not packing it, this is 0, and so this product is 0. So this summation is calculating the value of everything that I have chosen to take. So this is what I want to maximize. Then we've got constraints. So the constraint we discussed on the last slide, this weight limit, the left-hand side looks very similar to what we did for the value. So each item has a weight. I have this product, and this is coming up with the weight of everything that I've packed, and it needs to be less than or equal to some provided weight limit. This would be given to me. And then if we want to make things interesting, you could also say, you know, I can only fit 2 items, or you could have like an item limit if you wanted to. So I could just sum up all of my binary variables to count how many items am I actually packing and set that less than or equal to 2. So there's lots of different additional constraints that could go into there. So just so that we have more than one constraint, we'll play with this second one as well. So once we have these equations, this is really our whole constrained quadratic model. We have our objective and we have 2 constraints. So let's look at how this would actually go into an Ocean program, Ocean being our software tools. All right, so this would be the full program to run a knapsack problem with 5 items. Okay, so typical Python program, you're going to start by introducing a bunch of packages. I've got inputs that would be provided, like the value for each item, the weight for each item, my overall weight limit, and then n is just counting how many items there are. There are 5 items. So these would all be inputs from, you know, whatever the scenario has. So the first thing that I'm going to do is I'm going to create a binary variable for each item. So here I've put them just in a list, and n was the number of items. So I have, you know, binary variables 0, 1, 2, 3, 4 for the 5 items. These are just going to say, yes, I'm taking it, or no, I'm not taking it. I'm going to construct an empty CQM. I'm just going to initialize it so that I can build in my model. And first I'm going to add in the objective. So if you remember, we had on the last slide, the objective was this VIXI sum. So if I look at this equation, you'll see values I times XI, and this is a sum. So just like what we saw there, with the change that we made this negative. So remember I said, you know, the samplers are looking for the lowest valley. Our samplers always minimize. So to convert this maximize expression here, we just multiply it by -1 and it becomes a minimize. So that's what we did there. And this is the sum over all of our items that we could pack. And quick sum is just a function that we have to very quickly sum these things up. It works a lot faster than the regular Python sum for these objects, these binary variables we've created. So this is very clearly that math equation, vi times xi, summed over I through our variables. Next, we have the two constraints. So one was the weight constraint. So we did the product weight I times xi less than or equal to the weight limit. So here you can see, again, we have a sum of weights I times xi less than or equal to the weight limit. And I just to give that constraint a label so that I can reference it later, called max weight. Similarly, for adding up and making sure that we only have up to 2 items, I can just add up all of the binary variables less than or equal to 2. And again, I give a label that says max items. So those 3 lines build our entire model. Okay, so very, very easy. You can add in as many objectives, as many constraints as you want. You would just keep adding in constraints. If you had multiple objectives, you would combine them all into one objective. Oops. All right, so then to actually submit it to the hybrid solver, we define the sampler we want to send it to. We're going to send it to the hybrid CQM sampler. And so this is just, connecting to that sampler basically. And then sample CQM, give it the model that we're sampling, and your results will be returned in a sample set object. The sample set object has a lot of different information. So if we look at Oh, 0, 1, 2, 3, 4. These are just the names of our variables. And then we have 1, 2, 3, 4 samples that were returned. So each row is a different solution that we got back. So the first row says that we should pack items 2 and 4. And the objective function would have a value of negative 142. This solution showed up 3 times. This column is phi that you can see. This is a very important column, which tells you if the solution is feasible. So basically, were both of those constraints satisfied or not? And so in this case, they were not. So which one of the constraints was not satisfied with this solution? So we got a really good, very minimum objective value, but the constraints were not satisfied. So if those are hard constraints, then we would need to throw away the solution and not use it. In which case we go to the second line. So this one says pack items 0 and 4 for a value, our objective value is negative 98. This one showed up 36 times, so quite a few times. All of the constraints are satisfied. So this is really like our best feasible solution that we got. And then we have a couple other solutions where we just take one item, we take one item here, but this energy value, this objective function value is larger and we're looking to minimize. So this 98, this is going to be the best solution that we found. So if we look at those and translate them back into, our original, what does that mean in terms of number of items, the weight, the value, all that kind of stuff. So that first solution, the total number of items was 2, the total weight was 11, and the total value, our objective value, was 142. So our total items constraint was satisfied. We could have at most 2 items, but the weight was over. So if we go back to like the problem that we looked at, this weight limit that we provided was 10. And so that solution that we saw has a weight of 11. So it's not satisfying that second constraint, the weight constraint. The other ones, they do satisfy both constraints. And so we can see that this solution would be the best one that we found. Now, I mentioned like this is feasible column is very, very important, especially if you know that you can't consider a solution unless all the constraints are satisfied. And so we have built in functionality to filter out any infeasible solutions so that you can look at just the feasible ones. And so this is a really nifty trick that you'll see in a lot of our code examples where you can give it the sample set object that you got back and filter and see just the solutions that are feasible. All right, so we are going to do a little exercise. But first, any questions on that? I don't think I can see the chat, so. All right, so there was one question that said, could you repeat what is the quadratic equation solved in this example? So these are the equations that we looked at. And so you can see that this is linear, linear, linear. However, when you actually convert these statements into the right form under the hood, these are going to have quadratic components. So basically you can think about it as like this weight of selected items. If I choose one really heavy item, then that does impact the other items that I chose. There is that interrelationship. So under the hood, these ones do have a quadratic nature, but the way that they're written right now, where they're just like inequalities, they're just linear. There's another question that says, is there a limit to the size of vector, the xi's, you can set? Yeah, so for the CQM hybrid solver, you can have up to 500,000 variables. So I could have up to 500,000 items to choose for my knapsack. Now, if I was actually building in Python a model containing 500,000 variables, this way of doing it would be very slow. Like building the model itself would be slow and would take up a fair amount of space. So once you start getting to larger models, there's like standard Python efficiencies that you might want to take into consideration. But as far as like the model that you can build and send over to the hybrid solver, we could have up to 500,000 here. Then there's a question that says, is it operator applied to a function? What operator? Was that in reference to your earlier question on like where are the quadratic terms? Yes. Okay, so this part of our tools is open source. So you can go and look at exactly how it's implemented. Basically, when you have like inequality or an inequality constraint, when you go to run those on like the quantum computer or one of the other hybrid solvers, we have to model everything into one equation. You need to figure out how to express these as a minimization expression as well. And so that's where it comes into play. So basically you're converting inequality or equality statements into a minimization function. And so you would end up with like this side squared, you would have some slack variables and things in there in doing that. There's some code on our open source packages. If you go to D-Wave Systems is where the Ocean SDK is. If you look in the DIMOD package, you can find things on like add linear equality, add linear inequality, and you can see exactly how that's formulated. Alternatively, you can go to our docs and there's a link right to the function from the docs. That's probably an easier way, but that's probably the best way to see exactly what's going on there. Then there's a question, why does the solver return non-feasible solutions even if we have explicitly specified the constraints? Is it because of its probabilistic nature? Yes, part of it is because of the probabilistic nature. The other part is like if it depends on how firm your constraints are, right? So you have constraints that are hard constraints and you have constraints that are soft constraints. So a hard constraint is like in packing that shipping container, each box can go in exactly one shipping container. I can't put one box into at the same time. It doesn't make sense. A soft constraint would be something like when I'm building antenna towers, and if I place them too close together, there's some interference. So, you know, my constraint might say I want 0 interference, but in the real world, you know, some small amount is probably okay. So there's a little bit of a gap there in what's acceptable. And so sometimes by allowing some of those infeasible solutions, you might get something that's like acceptable because the solver doesn't really know what's a hard constraint and what's a soft constraint. All right, so there was a question. Okay, so for the add linear equality and inequality things, let me go and get a link for you. Docs.ocean.dwavesys. If you want to see how these inequalities and equalities are formulated, I'll do this and then I can send you a link right there. All right, so I'll send you this link, and if you click on source, it'll take you to the source code where it's implemented. All right. Any other questions before we do the next exercise part? No? All right. So I have set up some code on GitHub for us on my GitHub page. So here I'll paste this link. And so if you want to follow along, we'll go there, and we're going to use this knapsack right here. So I'm going to click on that. And so this is looking at code like we just saw on the screen. So it's importing the packages. It's the same exact problem instance, and you've got all the code right here. And then this is kind of where the slide code stopped. And then here you can see filtering for feasible, getting the first feasible one because that's probably the best solution, and then printing it out so that it makes sense for us, like what are the values and what are the weight. So just a little bit of like looking at our answers so we can make sense of them. So we're going to open this in the IDE. So last time we opened an example from the code examples in the IDE, but you can actually open any GitHub repo right in our in-browser IDE that will already have Ocean installed. So the way that I'm going to do that is for any GitHub URL that has like a repository and stuff, you can just add a prefix. It's just this prefix. So like you can do your own repositories, you can do someone else's repositories, and you basically just stick this prefix right up against it and hit enter and it'll open. I think I did also put a link down here. So, you know, if you make a typo or anything, like you can just click on this link and it should open in your IDE. If you weren't already logged into Leap, it will ask you to log in. And so now this is opening up a brand new workspace that has Ocean and everything installed, connected to the solvers that my Leap account has access to. And then this code from the repository and everything in that repo will be there. So this is a great way to like work on your projects and make updates and everything. The workspaces also save your work. So when you close the workspace, it's going to save everything that you did right here in the workspace, and you can come back to it later from your Leap dashboard, you know, that IDE workspaces button at the top. All right, so here you can see I've got everything that was there, the README file that we saw, and then this is the code that we were looking at on the slide. And yeah, so everything that we saw before, defining the binary variables, initializing the CQM object, setting the objective, our weight and our number of items constraint, running it on the solver, and then looking at the answers. So to run code in here, there's this nifty little green triangle up here, and this is just the run button. And so it's going to run the file that's open and run this Python program on the quantum computer. Well, the hybrid solver and the quantum computer. All right, so here you can see my results, and there's a lot because it didn't like aggregate them, but you can see most of these have this energy value 98. That was that best solution that we got on here, was this total value of 98. So if I look at this, this is corresponding to the same best solution that I saw. You can see these are all choosing items 0 and 4. And then scrolling down, you see some that are a little bit different. So not as good. And then a nice visualization of what the solutions were. So the best solution that I found were to choose items 0 and 4. So I'm not choosing items 1, 2, and 3. And their values were 34 and 64 for a total value of 98. And their weights were 3 and 2 for a total value of 5. So this code, like I said, it takes everything that we did on the slide, and then it also uses this filter. There's also an aggregate function. So if you didn't want to see like all of these number of occurrences 1, and you want to see it in a more compact form like what we have here, I can just do filter sample set dot aggregate, save, and then run again. And it should aggregate them into a more condensed form. So this is running on the hybrid solvers, which are based in North America, and they use the Advantage backend, which is in Vancouver. And so you can see it's very, very quick. So it's very real time. You get quick access. So you don't have to like sit around and wait. You can really work on your problems and try tuning different parameters, try adjusting your formulation, seeing what works to get a better solution. So here you can see I have this nice aggregated sample set now, and it's much easier to read. All right, any questions on that? Did you all get that to run and get that to work? Any issues with like the IDE or anything still? I know some people were having trouble opening the last one. No? Okay, then I think we are on time for our first break, a little early. So we'll take a break and reconvene at 11 if there's no questions. Or Daniela, do you want to just break for 15 minutes and come back early?
No, I think that we can have a break also right now if there is a good timing, and we can start again in 15 minutes.
Okay, so we'll start in 15 minutes then.
Yes, yes, yes.
Okay, perfect.
Okay, now in the meantime, I will try to go out and log in again in order to see if you can see me later.
Okay.
Because I never fixed it. Okay. So see you in 15 minutes. Thank you, Victoria. Very, very clear, very interesting.
All right.
And we will come back in 10:55, something like that. Okay. See you later.